Okay, where were we? Okay, so if you see this one, this is your e-learning. Okay, e-learning, blah 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 here until where is it? Okay, here. So I share to you guys the additional class. Okay, the session for the additional class. And then I also share the chapter 2 part 2 continue. Okay, which is about the electrical parts. Okay, the electrical parts. So please listen to that. Okay. Oh, okay. This is what I can do. Okay. Where I start to explain about the Fourier series. Fourier series application in circuit, inductor, resistor, inductor, and capacitor. So this one, for example, okay, I explain and until resistance circuits. Okay, I provide some explanation. This one. Sorry, what is this one? Oh, okay, never mind. This one is okay. So I explained about this one, okay. The application in the circuits, and then I ask you guys to relate, okay. And I ask you guys, and then I provide some explanation on the L and C. Okay, this one is already take some time, about 1 hour, just to explain this last time in the recorded. So if I to record L and C, it will become much more longer version, and maybe you guys will be like complaining. Last time student complain my video too long, but for me, I provide video a bit long because my intention is to give you as much as information. Of course, you know, sometimes you give long, student complain. You give shorter version, also student complain. That one is normal. Okay, we cannot satisfy everyone. Okay, so here the L and C circuits. Okay, I provide some brief explanation. Okay, and then you guys may try this one for R and L circuit. You try for all, and then there is R and L circuit. Please check. Okay, please check because I didn't go through on this a bit on this one. So there might be error with 200 pi. Okay, there might be error with 200 pi. Okay, how you know there's error or not is it for you to try first. Okay, to try first resistor circuits, to try L circuit, C circuit, R and L circuits, and then you see later on there might be some error with 200 pi. Okay, 200 pi. So we finish with that. Okay, this is chapter 2 part 2. Okay, now we're going to chapter 2 part 3. Chapter 3 part 1. Okay, chapter 3 part 1, which is Fourier transform. Okay, which is Fourier transform. So did you have the lecture 3? Did you guys have the lecture slide? Chapter 3 part 1. Do you guys have this one? Did I give you guys? Okay, good. Okay, so I continue. Okay. So all the while that you learn about Fourier series. In chapter 2, you learn about Fourier series. It's a series, so it is actually periodic waveform. Okay, and then you learn how to convert for this periodic waveform from time domain to your frequency domain. Okay, and then Fourier transform is the a bit different but still the same. Is involving the conversion. Okay, from time to frequency domain, and vice versa, which is frequency to time domain. Okay, however, there is a slight difference. Okay, so for this chapter 2, chapter 3 part 1, okay, for today, we will touch on the introduction and definition of Fourier transform. Okay, actually I managed to finish this with section 3 today, and we finished earlier. So I hope that we can finish this also today and finish earlier. This 3 and 4 will be asynchronous. Will be asynchronous. Okay, so introduction. Okay, recall from the previous chapter that we learned. Fourier series, the word here Fourier series, transform the time domain for continuous. Okay, so we learned it's about continuous in the previous lecture. Okay, in the previous lecture of chapter 2, into frequency domain, where we change, transform the time domain expression of continuous into frequency domain which feature a series of spectral lines separated by equal interval. Okay, this one maybe the words maybe a bit blur, but I think you guys understand what it is. Okay, last time when we learn about from continuous, okay, continuous Fourier series, then you learn to transform it to the spectral. Okay, so this one is equal interval. Okay, equal interval. If this is omega, this is 2 omega, for example. So this is equal interval. Okay, so this is we call also spectral lines. We call spectral lines. Sometimes we call it line of spectrum. It's just the same thing. Okay. Spectral lines separate by equal interval of frequency of different amplitude and phase. I think this one you guys also familiar, where this one is can be our amplitude. Okay, and then you also need to plot what? You also need to put your phase. Okay, at the same time sample. Okay, and Fourier transform is similar process, similar where we also do transformation. However, it is from non-periodic, okay, means not repeated signal into frequency domain and vice versa, which will lead to continuous, okay, spectral distribution at all frequency, not just the harmonics. Okay, so Fourier transform, okay, the same case but only for the non-periodic. For example, only this one. So it's non-periodic. So how we will convert it to become spectral lines. Okay, spectral lines. Okay. Okay. So far so good. Okay, it's actually convert a non-periodic. Okay. So why do we need Fourier transform? Okay. Sometimes it is easier to study and manipulate the signal in frequency form. Okay, for example, there is the same reason as well. Okay, for example, if you have one signal like this, complicated like this, okay, in time domain, but if you to convert to frequency spectrum, you only have one line. So it is easy to manipulate this one, then to manipulate this one or to analyze this one. Okay, so spectral line is if like you are looking from here, right? Okay, you're looking from here, so it's just like a one line. Okay, so easier to study and manipulate signal in frequency form. Many applications of frequency Fourier transform in electrical engineering, such as filter design to reduce noise, signal processing to restore. I'm not sure if you guys study signal processing. Okay, and signal modulation. Okay, signal modulation to transmit low frequency to high frequency. So I think you guys not yet study. Okay, this one, the signal modulation is about principle of communications. Okay, principle of communication. If you go to your website, because I want you to appreciate, so that you guys sometimes don't study blindly. Okay, here. So go to structure. You learn signal and system here. Okay, and then later on you will learn principle of communication here. This one. Okay, which require this one, your signal and system. So communication principle is the advanced course of signal and system. So you will use some skill from here to be able to sit for your communication principle. Okay, so this one must be at least pass. Okay, so I think this one maybe this one is next semester. Not sure. Maybe this one I teach also this subject. Not sure. Depends. Maybe you will get me also, because my field is telecommunication engineering. Okay, so maybe I'm the one teaching this in later on. Okay, but you always have choice to choose other lectures. No worries. Okay, we have a lot of section. Okay, now definition of Fourier transform. Okay, Fourier series is used to get the frequency spectrum of periodic signal. Okay, However, when the period of signal increase, the line or spectral line will be closer together. If the period approach infinity, signal become non-periodic and the line will be combined to make a continuous curve. Okay, blah 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 like that. Okay, you can read, but I just want for you to understand. So if we have time, okay, if we have time, this one, okay, this is your time. Let's say time 1, and then you have another signal, another similar signal, same shape, but if you increase the time now, okay, if you increase the time now, this one is T1 and this one is T2, okay. So you know that T is actually inverse to your F, am I correct? Inverse. So for F over 1 over T, okay, if you increase this signal, I mean if you increase the complete period, for in this case is T1 greater than T2 greater than T1, okay. So if you increase, you will notice that your frequency will be decreased, okay. So slowly, when you change the signal, okay, when you change in the spectral line, this one will be much more closer to one another, okay, much more closer, the spectral lines, okay. So then you increase further, it become more closer, closer. So until it look like as if it's like a continuous, okay, continuous curve in frequency domain, okay, in frequency domain. This one is in time, okay. So it is close together until it is like a continuous curve, okay. So pretty much explain what I explained is actually the same as the figures here, okay. So first, if you see a signal with a period of t, then 2t, 3t, 4t, and 5t. So you have like very short duration, which is t, 2t, and so on. So this is the corresponding spectrum, okay, spectral lines. So something like this. Then you notice that you increase the temperature, the period further. So from t here, now you have your t like here, okay, means increase. So when you increase the period, you will notice that your spectral line will be closer, okay. Then you increase much further the complete period of the signal, then you have more closer signal spectrum. And then when signal pass, when you approach infinity, for example, your t is maybe this one is 1 second, for example, this one is 1 second, and then imagine, just imagine, maybe not correct because it's not infinity. Infinity is limitless value. We cannot have value for infinity, right? So for example, this one is 1 second, and this one we increase the period until t 100,000 second, okay. So it will look like this, okay. So you can see the trend, okay. The more when you increase the period, the spectral line will be closer until at some point when it is approached the infinity, then the corresponding frequency domain spectral line will look like a continuous curve, okay. So this is a Fourier transform and inverse Fourier transform. So you have your ft, okay, you have your ft, you have your vt in time domain, you have your v omega, okay, which is in the domain, frequency domain. So there is process like this, okay. If you have v in your time domain, then you have your v big, you make it capital, you must see the difference, okay. You must see the difference. This one is small v, this one is big V, okay. So to convert from time domain to frequency domain, it will be Fourier series, okay, for the non-periodic. Then you want to convert back to this time domain from frequency domain, you need to perform inverse Fourier transform, okay. Then if you want to convert, okay, Sorry, sleepy. Okay, if you want to convert from VT to omega to in frequency domain, okay, you notice that okay, there is VT and you need to couple it with negative j omega t dt. Okay, and from negative infinity to infinity, this one sometimes vary, depends on the question. Okay, but this one is like VT times negative j omega t. If you want to convert, this is standard. And if we want to convert back to our frequency domain, okay, to our time domain, okay, we need to perform inverse Fourier transform. Then we will have the fixed 1 over 2 pi here and ej omega t d omega. Okay, you see here, d omega. So you guys may refer to your appendix, okay. You guys may refer to your appendix. Where is appendix? Where is my appendix? This one. Okay. So you guys may refer to your appendix. So this is Fourier series. This is table of Fourier coefficients. This one, okay, Fourier transform. So you can see this is it's like a general formula. Okay, when we want to convert to our frequency domain or spectral lines, so you have d omega here. Okay, this one, if we want to convert back to the time, okay, this one is inverse Fourier transform. This one is if we want to convert to Fourier transform. Okay, this one is, you see there is a constant value here, and not constant, consistent value, which is epsilon ej omega t. Okay, this one is 1 over 2 pi and ej omega t dw, and this one is dt. Okay, so now we go to the Fourier transform for impulse function. Okay, so means that you have in time domain, an impulse function. So what is impulse function? Okay, if you refer to the previous lecture, okay, you may refer to the previous lecture. Okay, impulse function is actually we have value at only one short period of time, and the rest will be 0. Okay, and the rest will be 0. So here we want to convert from the time domain to the frequency domain. So you need to put here f to Fourier transform. We have vt and infinity from negative infinity, and vt ej omega t dt. Okay, so if you notice, we only have value at t equals to 0. Okay, so what is ej omega? Okay, what is e? Because we only have value at 0. 0. So you have j omega t. Okay, regardless of negative or not negative. If you have 0 here, so you will have E0, right? E0. So E0, whatever with the power of 0 will be 1. Okay. Okay, so you see here, Fourier transform. Okay, then you obtain v omega. Okay, you obtain your v omega. So this one is actually like 1. Okay, like 1. Okay, because just now, right, E1. Okay, because it's an impulse function. Okay, and then you obtain your v omega. Okay, and then Fourier transform of this impulse, okay, is equals to 1. Okay, is equals to 1, and your vt is actually your delta t, this impulse. Sorry, maybe in your slide it's not, there is like a Messi, not Messi Elliot, Messi. So this one is f on top. Okay, on top here. Okay, Fourier transform. So delta t, if we want to do the Fourier transform, we will get 1. So here, so that's why you obtain 1 here. Okay, this is the original in time domain, but if you convert using Fourier transform, you will obtain a like a DC value, like a DC value, like just straight line. Okay, straight line. And then Fourier series for rectangular signal. Okay, for rectangular signal. So you see, this is periodic. Okay, you see, for example, periodic. Okay, wait for one. I off my aircon to cold. Okay, so if you see this one is periodic, means repeated waveform. I think you guys already familiar with this. Okay, using the Fourier series, okay, you will obtain something like this, sinc function, envelope. Okay, you will learn. So this is for the periodic waveform. Okay. Okay. So example 2, Fourier transform for rectangular signal. If you see is only one periodic signal, we don't have others. Okay, means we don't have it as a repeating unit. So go to your appendix again. Okay, where is the appendix? Okay, go to your appendix that we see for rectangular signal here. Okay, you see negative tau over 2, tau over 2, and A. Okay, then the resultant signal, the result converted frequency domain will be AT sinc omega t over 2. Okay. Okay. Using the Fourier transform, the frequency spectrum will be okay. So please refer to your slide because I'm going to use touch screen. So I'm going to I'm going to use this. Okay, refer to your own slide. Slide page 1. I'm a bit forgive me. Okay, the slide look like a bit messy. But as long as you understand what is it is more important. Okay. So wait. Is it clear? This writing? Is it clear? Is it clear, this writing? I'm not sure is it clear or not, because is it clear? I hope it's clear. Okay, clear. Because I need to save space. So, okay, now we want to convert. We want to convert this rectangular signal. Okay, so you will have the omega here. Okay, then use integration. Okay, integration from negative infinity to infinity first. Okay, the standard formula. Okay, you take the standard formula first. Then you have Vt. Okay, Vt. Then you have your the standard one inside. Okay, standard one inside is j omega t. Okay, dt. Okay, then you see from the table. Okay, from the appendix. So we have to use like negative tau over 2 and tau over 2. Okay, refer to the appendix. Then we have our amplitude here, which is our A. Okay, means that from negative tau over 2 until tau over 2, we actually have A. Okay, then we have E, negative J omega t, and our dt. Okay, then you do the integration parts. You do the integrations. Okay, this one is actually a constant. So if it's constant, we can just take it out. Okay, and then you will do the integration. So E negative j omega t, and you have a negative j omega. Okay, the result of your integration. Then after that, you have negative tau over 2. Okay, and tau over 2. Okay, and then here comes your skill of Euler's theorem again. Okay, you take it out. This one A negative j omega. Okay, then what equation left inside is actually E Tak nampak. Wait Okay. Then you have a negative. You take out the negative. You take out the negative. Maybe I should put like this so that it's clear. Okay, negative. Okay. So then you will have a negative j omega tau over 2 minus e j omega tau over 2. Something like this. And then you know, right, from your Euler's theorem, okay, what Euler's theorem said that sine what? Sine something and this one minus something and 2j below, right? Okay, if you guys don't remember, you refer to your table or your previous lectures. So we have 2j here. Okay, we have 2j here. Okay, so we try to relate now with Euler's formula. So you see you have j here. Okay, you have your j here, and then you have you need to introduce w2 there. So I'm going to here. Okay, so if you put inside, okay, if you put inside the negative j, if you put inside 1 over negative j, okay, 1 over negative j, so you will end up like, for example, a over w, okay, and then you put the negative j inside, you will have j here, then you have e j omega tau over 2, and because you put negative inside, so it will be, this one will be reverse order. So you become this one negative, negative, positive, then negative, positive will be negative. Okay, something like this. And because you want to relate with your Euler's theorem, okay, you put here 2. Okay, you put here 2. Then what you have later on, this one is actually equal to sine, am I correct? Okay, this one will be equal to sine omega t over 2. Okay. And then later on, you will, until you solve this, okay, you solve this until the end, okay, you will have sine omega t, omega tau over 2 equals to sin omega tau over 2 over omega tau over 2, okay. So this is how you get it, okay. This is how you get it. Where is the appendix? Okay, this is how you actually get this. 80 sine omega t, omega tau over 2, okay. So the next, once we have solved the equation, the next step is actually to plot it. Okay, just like our previous chapter, you need to plot or sketch whatever name they give you, but there is a graph needed. Okay, so you can see this one is the amplitude in modulus. Sorry, there is error also in the slide. Okay. Not that it's not error. It's like the thing is moving around. Means it's, wait for a while. I take this one. Put to my slide. Okay, so the next is actually for you to convert, okay? Not to convert, to plot, okay? When you plot, of course, this one, if you see, this is in magnitude. In modulus means always positive, okay? Always positive. The initial line will look like this, right? For the sinc function, okay? But now because we are using amplitude, okay, we are using amplitude with modulus, okay, for example, then we will have a all positive answer. Okay, and then the next is what it will not complete if we plot the graph without plotting it phase spectrum. So you need to plot the phase spectrum as well. Okay, phase spectrum as well. So in this case, like this. Okay, the difference with negative pi. Okay. So next is the example Fourier transform for exponent. Okay, you see, for exponent transform, for exponent. So again, we look at our table. If we look at our appendix. Now, okay, you can look at your own appendix also, so that you know where to find them. Okay, so where is the this one is Fourier transform pair. Okay, now we want to convert our exponent signal. Okay, for example, this one. Okay, this one is decreasing exponential function. So we need to, you guys need to know how the normal exponent look like, the standard one, and this one is actually what shown in the appendix is the decreasing one. Okay, the decreasing one, you actually can see how it decreases because you have negative here. Okay, you can see that you have negative here, and then you have a here is amplitude, mean this one is the highest. Okay, this one is the highest. So again, look at your slide because I'm going to demonstrate using pen. I think it's slide number example 3. Example 3. Go to example 3. Okay. So what example 3 shows is find the Fourier transform for the signal Vt blah blah blah. Okay. So if you see here, Vt equals to A E minus sorry, where it's too small the slide. Okay. Where is it just now? Okay, E A T ut. Okay, for a greater than 0. Okay, if you see this one, okay, there is a function of unit step there. Unit step. So what do you understand about unit step first? Unit step, what value what is the value for time 0 and to negative infinity? What is the value for unit step? Only Abdul Rahman know, the rest don't know. The rest what? You know what or not? The unit step. The negative region, what is the value for unit step? Good. Okay, at least okay. So you have here is you have some value and the rest will be 0. Okay, so that's why you see here. Okay, that's why you have this one for a greater than 0. Okay, means we don't have value at less than 0, right? Okay, then we go to the solutions. Okay, solution, we want to integrate. We want to convert time domain to the frequency domain. So you put Fourier transform, okay, of your exponent a e negative at. Okay, forgive me if there is some typo because I'm depending on the slide and also I'm writing. Maybe I missed something. Please let me know. Then you start from 0. Okay, why I start from 0? Because we only have value from 0. Okay, because we are using unit step here. So until your infinity, then you have your a, then you have negative a at. Okay, and e negative j omega t dt. Okay. So then the next part is actually you can do the if you refer to the slide, this one actually you can edit if you can edit also. then you will come across that when you settle this one, okay, this one when you integrate, negative a will be outside. Negative a will be outside. So you put the a outside first because it's constant, infinity. And this one you can actually put them together, at negative at negative a, sorry, negative a plus, not enough space. Negative, you put the negative outside. Okay, negative. And then you have this one, a, you just factorize, right? A plus j omega t. Okay, and then you put the limit, because your limit, sorry, not yet limit, sorry, laju pula saya nak habis sorry, suddenly become so fast. So this one is dt. Okay, then you do the normal integration with the limits. Okay, a you can put outside, negative a. Okay, and then integrate 1 over a plus j omega. Okay, and then e negative a t, a plus j omega t. Okay, with limit of infinity until 0. Okay, the limit, something like that. Okay, then you will have your final in the frequency domain, which is v omega equals to a plus a small a plus j omega. Okay, so refer to your table. Okay, so refer to your table in the appendix. You will actually will see that see a blah blah a e exponent ut is actually equals to this. Okay, so go to your what we call it, appendix C.2b. Where is it? Oh, okay, this one. Okay, you can see this one. And then you can see here, this one is like inverse, means you have like a double. Okay, so from here you have this value initially here, then you have another also value here. So your resulted Fourier frequency spectrum after Fourier transform, you get this one, the frequency domain. Okay, you can try this later on at home. And then this one, you have this, you get some mark here. So do you know what this mark is? I think you guys should learn in your secondary school, or maybe in your before coming to this class. Okay, do you guys know about this? What is this? This one. Good. So this one is factorial. This one is factorial. Okay. And then once you obtain this one, the next is actually to get magnitude and spectrum. Okay, magnitude and spectrum. So simple for the magnitude is a over square root of a square plus omega square. Okay, a square plus omega square and a. So this is your magnitude. How you get your phase is actually inverse tangent of omega over a. Okay, so this is how you get your phase. Okay, and then this is actually in terms of combination of magnitude and also your phase. Okay, e negative j inverse tangent and so on. Okay, then the next step is to compute. Okay, to plot. Okay, this is the original the signal in time domain, and then you will have after you transform your signal, you will have two the same. You have amplitude, you have phase, you have to plot, right? So you can test this one. Okay, you can test this one, this this modulus. Okay, you test with increasing omega, what you will get. Okay, here. Okay, you can test. You will notice that you get a shape similar like this. Okay, Then this one is your phase, okay? So phase is from pi over 2 to negative pi over 2, okay? Because, and then if you notice this one is what? Inverse tangent, right? This one is inverse tangent. So what do you think this one? This is shape of what? What is the shape? This one. What you call this shape? Do you guys know this? This one is what? This like an inverse tangent shape, huh? Okay. The next part is the inverse Fourier transform for impulse function. Okay. So please refer to your slide because I'm going to do the same thing. Okay. I'm going to demonstrate in the slide. I mean my pen. Okay. Okay. So now this example 4 is actually, before this we learned about how we're going to convert from time domain of non-periodic waveform, non-periodic waveform to frequency spectrum, to the frequency counterpart. Now we want to do the inverse process, which is inverse Fourier transform. We're having this signal in the omega, in the frequency domain. Now we want to convert it to back, we want to convert it back to our time. Okay, kan? Susah payah convert ke omega, sekarang nak ke time pula. Okay, but that is how you manage to convert to omega, and sometimes in some cases you need to convert it to time again. Okay, so that's why we need this what we call is a Fourier inverse Fourier transform. Okay, okay, refer to the slide. Refer to the slide. So I'm just doing here F. Okay, you see, you must write like this to show that this one is actually inverse transform. Okay, so inverse Fourier transform. Put in bracket. Okay, this one is for impulse function. So impulse, you know, right? Impulse is this one. Okay, you obtain the impulse in the omega domain, in the frequency domain, and then you see the standard formula just now is the standard one, 1 over 2 pi. Okay, and then from infinity to infinity. Okay, and then you put your inverse, you put your impulse here. Okay, and then the same couple here. Okay, the same couple that must be to put together. Okay, this one. Okay, so if you notice for the impulse function, we only have value at 0. Okay, we have value at 0. Okay, if you notice from the slide, we only have value at 0. Okay, so if we put this 0, regardless is negative j or j, but if it's 0 here, what do we have here? Anyone? Okay, so we have value of 1. Okay, we have value of 1. So that's why this one is just like 1, because it's Fourier transform. Okay, I mean because it's impulse. So then we will left with 1 over 2 pi. Okay, 1 over 2 pi and omega w. Okay, and equals to 1. Okay, not equals to 1. I'm sorry, a bit error there. This is equals to 1, not this one equals to 1. Okay, and then you will notice that this equals to 1 over 2 pi. Okay, 1 over 2 pi. Then your impulse is actually 1 over 2 pi. Okay, and then you rearrange, you will get 2 pi. Impulse of omega in omega, not t, is equals to 1. Okay, too small. Okay, so now you have actually 2 pi 2 pi here. Okay, 2 pi omega whatever here is equal to 1. So when you plotting, okay, when you plot, okay, you have here, remember this is in frequency domain. Okay, is in frequency domain, and it is 2 pi impulse function of omega. Okay, so undergo inverse Fourier transform to get the time domain counterpart. So you have t here, time domain, and then remember here is vt. Okay, so it is actually just like a DC curve, just like a DC line, which is 1. Okay, that's how we get it. Okay, that's how we get actually inverse transform from impulse function. We will get the straight lines. Okay, go to your appendix. Okay, go to your appendix. Try this one yourself to prove it's possible. Is don't take as it is. Okay, don't take as it is. This one. Okay, if you have time, you can try to prove or whatever. If you don't have much time, maybe you can see YouTube, actually how they demonstrate how you obtain this one to this one. Okay, so that you will appreciate the knowledge more. Okay, before you finish the class, okay, today we'll finish a bit earlier. I will provide asynchronous, okay, for remaining chapter. Okay, chapter 3 part 2 will be asynchronous. Okay, where's this one? So this one is your class, 2073-04. Okay, the same like before. Just mention what you have learned for today. Okay, for today's lecture, and then when majority have responded, I will provide the recorded live lecture. Okay, today we finish a bit early. Okay, later on we will go to chapter 3 part 2. And then I think we will combine section. We will have additional class to discuss about past tense. I'm not sure which past tense this I give you guys. Which one? Okay. I hope that at least you have. I hope because we need to see your progress also. I hope we can at least discuss two set of past question for test. Okay. So we will discuss this, but maybe Chinto and Adi will manage the class. Okay. So test 1, question 1, chapter 1, question 2, chapter 2. Okay. And quiz 2 is coming, which is on the this one. Okay, on the next week. Okay, I think it's 2021 is when? 21 is on Sunday. Okay, of course, and then it is 24 hours. Not 24 hours. I will open from what 12:01 a.m. until 11:59 p.m. So you manage your own time. Okay, you have 5 questions, 30 minutes, and your submission time will be 2 minutes. So don't use the remaining 2 minutes to actually still solve the question. Because you must make sure that you submit, because this time no more no more second attempt, and you must submit. Okay, so 2 minutes, just submit whatever you have. 2 minutes, and I'm sure you will not get zero. I mean, I'm sure that you will not answer anything, because there is multiple option question. Okay, and then this class, I'm not sure this class, contrary with section 3, section 3 have long gone, very long time ago already finished submission. So I'm not sure, after 24 hours given yesterday, 2 have submit, but there is another one didn't submit the quiz 1 working step. You know yourself. You know yourself. I don't have to mention the name. You know yourself. Later on, you will see that your quiz 1 will not get any mark. Okay, because I hold your mark, because you didn't submit working step. Okay, of course you maybe ignore right now, because I think you ignore because I already repeated so many times, even yesterday also, even Ching Tong already have to mention, but still student don't submit. I'm not sure. Okay, so this one of the student will be, I will hold his mark, his or her mark. I'm not sure who, because I need this working step as a record purpose. Even though we have e-learning, I need to keep it, because in future maybe we need to compile students file, then maybe I will need also your working step. Okay, with that we finish. Okay, try to do tutorial 2 and tutorial 1 and pass test. Okay, your test 1 is coming next week. Okay, thank you very much. You may leave this class.